Hello guys, welcome back to the second part of our lecture. In this video, I'm basically going to talk about some of the properties of regular expressions. Now this is going to be a fairly short video, so I shouldn't be bothering you too much today. Actually, I can't believe how short this video is going to be. Anyway, before talking about the properties of regular expressions, I want to talk about a couple of properties of regular language itself. Now, the first property. If there are two regular languages, the union of those two languages is also going to be a regular language. Now we already knew that because the proof of this comes directly from the definition of regular expression itself. In fact, we saw this in our last video, which is basically the first part of this very lecture. Now this is new. If we have a regular language, the complement of that is also a regular language. So if we have a set of strings which is regular, the complement set is also going to be regular. The proof is pretty neat, which I'm going to show you right now. I'm going to use the concept of an abstract finite state machine, and I think you are going to enjoy this. Okay, so some of you may remember this diagram. We showed this diagram when we were talking about how a finite state machine works. So in here, we have a finite state machine. We are calling it M. We have an alphabet for this machine. This machine can process any string you can create using the symbols of that alphabet. Some of those strings are going to be accepted by this machine, and this set of accepted strings create the language of this machine. We call this set the language of M, or in short, L of M. All the other strings must be rejected by the machine. So any string that is not accepted is by definition rejected. So any string that is not a member of L of M is a member of this. So what is this? The complement set, L of M prime or L of M bar. What we have to prove is that if L of M is a regular language, L of M bar is also a regular language. Now to prove that, first try to recall the very relationship between a finite state machine and a language that is regular. If you remember, every regular language in the world by definition has to have some finite state machine somewhere that will accept it. So for every regular language in the world, we can create a machine M and call that language L of M. Now, I'm going to create another finite state machine, but I'm going to use this one to create that. Let's call this machine something interesting, say Arsenal. Alright, so our original machine M, and on top of that we have created another machine that we are calling Arsenal. We have built Arsenal to follow the following logic. Whenever M accepts something, Arsenal is going to reject that. And whenever M rejects something, Arsenal is going to accept it. So is Arsenal a finite state machine? Well, yeah, because all we did is took a finite state machine and added one more step. What we are doing is, whenever the original machine M is producing a result, we are just inverting it, right? So whenever it is accepting something, I'm rejecting it, and vice versa. Now, what is the language of Arsenal? The language of Arsenal is going to be L of M prime, right? So, as Arsenal is a finite state machine, and the language of this machine is L of M prime, then L of M prime must be a regular language by definition of finite state machines. So, if L of M is a regular language, it is always possible to create a machine that will accept just the complement set, which is proof that if a language is regular, its complement is also regular. You have to admit that proof is kind of interesting, right? Okay, moving on. Now, based on these two informations, that the union of two regular languages is regular and the complement of a regular language is regular, I'm asking you this question. Is the intersection of two regular languages regular? Can you prove that? There should be an S here. Can you prove that? I strongly suggest you to pause the video right here and try to prove it on your own. This is pretty easy. You don't need any fancy formulas or equations. The only thing that you will need, you were taught that in high school. So please pause here, and I'm going to move on anyway. So we are back to the properties of regular expressions. Now these are pretty straightforward high school stuff, so I'm not going to go over all of this. I'm going to show you just a couple of important things. First of all, we can see that the regular expression are commutative when it comes to the operator OR. So the order doesn't matter when you are ORing two regular expressions together. But the the concatenation operator is not commutative. So R concatenate M is not the same as M concatenate R. And I think you can understand why, because ABX is not the same string as XAB. So order matters when you are joining two strings together side by side. The second important thing is this property. What is the identity of an operator? The identity of an operator is when you use that in that operator and the result doesn't change. Yeah, that sounds confusing even to me. So let's give you an example. The identity of plus or addition is 0, because when you have anything here and you add 0 to it, the result doesn't change. The identity of multiplication is 1, because whatever you have, you multiply it with 1, the result doesn't change. Similarly, the identity of OR is the empty set, because if you OR any expression with the empty set, the result is that original expression. Similarly, if you concatenate any expression with the empty string, the result is the original expression. So empty string is the identity of concatenation. Now what is annihilator? Annihilator of an operation is when you use that in an operation and the result goes to 0. For example, the annihilator of multiplication is 0. It doesn't matter what you are multiplying it with. Whenever you are multiplying 0 with someone, this should be a 0, the result is 0. So whenever you are concatenating any expression with the empty set, there is nothing here, not even the empty string epsilon. The answer is always empty set. So empty set is the annihilator of concatenation. Idempotent, the next important thing. What is idempotent? Idempotent is when you use an operator repetitively and the result doesn't change. So here, when you OR R with itself, R is any expression, the result is R. Doesn't matter how many times you OR it with, the result will always be R. Alright, so next we have some identities of regular expressions, and all of these involve the closure operator. If you have an expression R, and if you take the link closure, it doesn't matter how many times you take the link closure. So R star is equal to R star whole star. This is the same as taking the link closure one more time, because the link closure itself is infinite. You can take as many R as you want. It doesn't make sense taking infinite twice. Okay, this one is interesting. If you take the empty set and take a link closure on top of it, it becomes the empty string. It no longer is empty set because the cardinality of this is 1. Okay. I kept saying that the link closure and the positive closure are not different operators. That's because the positive closure is just a derivative of the link closure. What does the positive closure say? It says one or more occurrences of R. If I write this, what does this say? I'm taking R at least once and then 0 or more occurrences of 1. So combined, I have R at least 1 times from here, and then 0 or more times from here. So combinedly, this is the positive closure. Now this one here is pretty similar to this one, and this one is saying m or n whole star is equal to m star n star whole star is equal to m star or n star whole star. So I'm keeping these 3 for yourself, these 2. I want you to verify this. Take any expression for m. Let's say m is ab and n is 1. Now verify these by yourself. Take m, ab or 1 whole star. See what you get. Take ab star. Oh, I kept a board for writing all this. Anyway, take ab star, 1 star and whole star, and then see what you get, and then verify that this statement is correct. Alright, so that's all the property I had for you. Now before finishing the video, let me just show you the proof of the question I asked you before. Let's assume that L is a regular language. Now we already know that the complement of this language is also regular. M is another regular language, and the complement of that is going to be also regular. We know their union is regular, so this is a regular language. And the complement of this regular language is also regular. Now does this look familiar to you? It should, because this is basically De Morgan's law. And what does De Morgan tell us? That is not Morgan. De Morgan's law. And what does De Morgan tell us? That this is equal to the complement of L intersection M. Now this double complement here will cancel each other out and we are left with L intersection M. So using the property of union and complement, we could prove that the intersection of two regular languages is also regular. The proof was pretty easy, right? All of you knew about De Morgan's law. It just takes a little bit of thinking. Anyway, that's it for today. It's a wrap up. In the next lecture, we are going to do some practice and see some examples of regular expressions and regular languages. Alright, until then, goodbye and thank you.